Okay, what we're doing are finding the zeros of polynomial functions. We're finding out if there's an even or odd number of a particular root to determine whether it crosses or bounces. We're looking at end behavior. We're finding y-intercepts also, and then we're making just a casual graph of that. It's not perfect, but we're just trying to get an idea of where it's going. Let me talk first a little bit about polynomial functions. First of all, poly means many, so we're talking about something with many terms or something with many pieces to it. Y equal x is the parent function of a line. Y equal x squared is the parent function of a quadratic. Y equal x cubed is the parent function of a cubic. Y equal x to the fourth is the parent function of a quartic. We could have another term with a square on it. We could have another term with the first power on it, and we could have another term with a constant. All of these are polynomial functions. They're polynomial functions because they don't have like a variable in the denominator, which would be a rational function, or a square root on a variable, which would be a radical function, okay? Or something like x squared plus y squared equal 1, which would be a circle, okay? Or parabolas and hyperbolas. So when we have this, these are all called polynomial functions, and this is a polynomial of the first degree, a polynomial of the second degree, a polynomial of the third degree, and a polynomial of the fourth degree. Even if this was to the second power here and that was to the third power there, which isn't in the order that we like, it's still a third degree polynomial. We would normally rearrange them in descending order of exponent. So it's a polynomial, then the degree is the highest exponent. Let me show you something. Remember that y equal x looks like this, x squared looks like this, x cubed looks like that. So its end behavior is the same as the end behavior of the line. Y equal x to the fourth looks like this, so its end behavior is the same as the end behavior of x to the second. So odd end behaviors all kind of look the same. Even end behaviors all look the same. But it would change as to whether it's positive or negative, as to whether the arrows go up, down, or down, up, or if they both go down or they both go up. Okay, so we've talked about that. If I had something like y equal 1 over x, that is a rational graph. It actually looks like that, okay? So you may realize that your polynomial graphs then, they look like this, or this, or this, or this, or this, right? They've got that they've either got a curve like this, or a curve like that, or the curve here. But it's all got a piece of that curve thing in it that's connected. If we had a radical graph like y equals square root x, the graph looks something like that. Okay? And that's a radical graph. All right, so there's some of the general idea of what a polynomial function looks like versus a rational function versus a radical function. Okay? And we talked about the end behaviors of polynomial functions. All right. Now, on number 3, they've given us a polynomial of the fourth degree, a fourth degree polynomial. And it's going to have 4 roots because it's an x to the fourth power. We do not know today from this course how to factor a quartic. We only know how to factor a cubic if you can factor by grouping. If you can't factor by grouping, we don't know how to do that. So what I did is I went ahead and gave you the first factorization of that quartic because you don't know how to do that part yet. The second part of that is a cubic that is factorable by grouping. Okay? So what we would start with here to find the roots, and we'll talk about that first since I'm there, and then we'll go back to end behavior, is we're going to have x plus 5 times x cubed. Let me erase that. X cubed plus 2x squared minus 9x minus 18 equals 0. So remember that to find the zeros or the roots, it is the values of x that would make y 0. And we know because it's a fourth degree polynomial, there's going to be 4 of those roots. Okay? Now, the only choice that we have right now in our ability bank of factoring this cubic is to factor by grouping. So we're going to assume that the teacher made that happen for us. So out of this left pair, we're going to factor an x squared. You understand when you've got the exponent situation, you choose the least one because that's the number they have in common. They have 2 in common. So we can factor out an x squared. So we're going to have x times what is x cubed. X squared times what is x cubed? X squared times what is x cubed? X. X squared times what is 2x squared? 2, so that factors into x plus 2. Everybody see how we got that? We said x squared times what is x cubed? X squared times x is x cubed. X squared times what is 2x squared? X squared times 2 is 2x squared. Yes. Yes. Sorry. Yeah. Yeah. So what can we factor out of the right pair? But we want to take the negative off because if we don't, there'd be a negative on the inside, which we don't want it there. You'll see why in a minute. So we're going to take off a negative 9. Negative 9 times what is negative 9x? X. Negative 9 times what is negative 18? Positive 2. You see that the insides need to match. And had we not taken off the negative, they would not have matched. Our goal in factoring was to have a common binomial here. Had there not been a common binomial, we would have realized that we could not factor by grouping. But there is. So that turns into that common factor of x plus 2, and the other factor is the pieces x squared minus 9. And then we still have that first factor that I gave you pulled off of an x plus 5, and we have equals 0. Everybody see we got that? So we factored the cubic portion by grouping. Now, we've got 2 factors, but then we've got the third one as an x squared minus 9. X squared minus 9 is the what? It's the difference between 2 squares. 9 is what squared? 3 squared. The difference between 2 squares factors into what? X minus 3, x plus 3, or x plus 3, x minus 3. What do you call those? Binomial conjugates. Binomial conjugates. And you need to put that in your memory bank. Here's the formula. A squared minus b squared factors into a plus b, a minus b. That's a formula to memorize. The difference between 2 squares factors into binomial conjugates. Put that in your permanent memory bank. So we still have the x plus 2, and we still have the x plus 5. Now, if we set them equal to 0 and solve, then the x here would be negative 5, and the x here would be negative 2, and the x here would be negative 3, and the x here would be positive 3. Everybody understands that? You'd say x plus 5 equals 0, subtract 5, x equal negative 5. So the roots are in parentheses. Excuse me, the factors are in parentheses, but the roots are in black. the roots are x equal -5, -2, -3, and 3. And they are the values of x when y equals 0. So in ascending order, we have -5, -3, -2, and 3 if I put them least to greatest, which isn't necessary. Now, the rule is if a root appears an odd number of times, it crosses. And if a root appears an even number of times, it bounces. The root -5, 0 appeared once. That's an odd number, so it crosses. -3, 0 appears once. That's an odd number, so it crosses. -2, 0 appears once. That's an odd number, so it crosses. 3, 0 appears once. That's an odd number, so it crosses. So it crosses at every point. So we found all the roots, and we determined whether those roots bounce or cross. We see how we got that. Okay? Now, we didn't talk about end behavior, and we need to. So, how do we determine end behavior? We look at the leading exponent. What's the highest exponent? 4. So it's a polynomial of the 4th degree. Is that an even or odd polynomial? Even or odd numbered exponent? It's an even. So that means what? They're either both up or they're both down. It is a positive even number, which means that they go, okay? So they do the same thing, and that same thing, because it's positive, is both up. Okay? Right, do you see how we figured out the end behavior? The 4. The question was, what's positive and even? It's a polynomial of the 4th degree, so we think about the 4. That's an even number. That means they're either both up or down. It's a positive 4, which means they're both up. Okay? The y-intercept is the value of y when x is 0. So if we put 0 for x back over here, all of that x junk would cancel out, and we'd get a -90, right? We've been showing our work on that. We've pretty well figured that out. If you zero out all the x's, you've got that number left. Okay? All right. Now, I'll let you, I'm going to pull the graph up just so we can see some stuff. So we'll let you remember on your paper what you have. Are you ready? All right. Now, the roots were what? -1, 2, 3, 4, 5. So there's an x-intercept, a root, a 0 at -5. There's an x-intercept, root, or 0 at -3. There's an x-intercept, root, or 0 at -2. And there's an x-intercept, root, or 0 at 3. That's what you can call that thing, right? An x-intercept, a root, a 0. So there they are. There's a y-intercept way down here at -90. We're just going to make up a spot and call it -90. We kind of did 1, 2, skip a few, 90. You know how you would doing hide and go seek. 1, 2, skip a few, 99, 100, and you find them before they get hit. All right, that's what we did. All right, that's how we used to do hide and go seek. 1, 2, skip a few, 99, 100. Got you. That's not fair. All right, anyway. That was the best part. I'm just kidding. Anyway, okay. So, end behavior. The end behavior was up, 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 down, up and down. What was it? Up, up. So, here's my extremes. Past this extreme, there's got to be an up. And past this extreme, there's got to be an up. There's my end behavior. So I've got I've got all my intercepts. I've got my end behavior. At the x-intercepts, we know if they bounce or cross. At the x-intercept of -5, it crosses. Now, here's what I want you to think. Is it going to cross that direction? Or is it going to cross leaning to the left, or is it going to cross leaning to the right? Well, look at the way this is going. It's got to be going like that's going. Now, we got to be moving to the right on this graph. So if we're going to go from there and get back up to here, we're going to have to go back up somewhere, right? And it's crossing here, but it's going to have to be headed that direction. And if I'm going to go back down and it crosses here, I've got to be going back this direction. So we don't really know how far down, so we just kind of throw that in there. We got some loop-de-loo stuff going in here, we know, right? Now this guy's got to go all the way down there and grab that y-intercept. And then it's going to cross there, as it said, and go back to that end behavior. It's probably not a hook like that, so that means I probably need to do a little better job of that, okay? So that gives us a general idea of where that graph is going. Any questions on number 3? Well, the y-intercept was -90 the first time. Okay, here's the deal. I'm going to just kind of throw these anywhere. We had this. We knew this did this. We knew this did this. And we knew somewhere in here there was a y-intercept. Okay? I know that it crosses at this point. Look at the direction your line's going, so it has to do that. But I've got to go back up. Well, that means if I'm going to go back up, I've got to turn somewhere to go back up and cross. Now, I don't know how far down before I come back up. All I know is I've got to come back up. Yeah. So you can go as far down as, we're just guessing how far down, okay? And then I realize that if I'm going to come back down to here, I've got to turn somewhere up here. I don't know exactly where. But then I've got a y-intercept sitting down here I got to go catch. So I got to go grab that thing, and then it's coming back up. The amount of up and down is a guess, except for the y-intercept. It's locked in, okay? Any questions on that? Okay. Obviously, to figure out more, we would need to plot more points, right? Build a table and just start finding points. All right. Now, this is an x to the 5th. It's a pentapolygon, or a quint. Quint is 5, okay? So it's a penta or a quint-agon. Pentanomial, do what? Or quintinomial, do what? Yeah. So the question is, why did I already give you all the roots? And the reason is, today we don't know how to factor that. And I could have given you the first 2 roots and then left you with a trinomial that you could factor by grouping, but we've already done that. So I just wanted to show you something to the 5th, even though you don't know how to break that thing down into its roots. But we will, within the month, know how to break that down into roots. We're just not there yet. So we're opening your eyes to something that we've got to learn more about. So I went ahead and gave you the roots. Now, the end behavior. This is a what? 5th degree polynomial. That is an odd degree. That means the behavior is up, down, or down, up. They're different, right? And it is a positive, so that means that it is an up, up. And in other words, it leans to the right. Like the slope of a line. If a line has a positive slope, it leans to the right. If a line has a negative slope, it leans to the left. So the fact that that's a positive gives us the idea that it leans to the right. And when I'm talking about positive, I'm not talking about the exponent. I'm talking about the coefficient of x, which is a +1, right? Not the exponent. So my end behavior, it's odd, so it's the characteristics of a line, except we do know it's going to be a curve, like, right? But the end behavior is the line behavior with a positive slope, which means it leans to the right. So that's the idea we have in our mind. The y-intercept is the value of y when x is 0. If we were to put zeros everywhere there's an x, all that would cancel out and we'd get a negative 36. Okay? Now, the root of negative 2 has appeared how many times? Twice. That's an even number, so what does it do at the negative 2? It bounces. If the root appears an even number of times, it bounces at that root. The 1 appeared once. That's an odd number, so it crosses at that root. The 3 appears twice. That's an even number of times. If the root appears an even number of times, then it bounces at that root. Okay? So it's going to bounce at negative 2, cross at positive 1, bounce at 3. We say we got that. All right, I'm going to shift this up. My y-intercept was way down here, somewhere at negative 36. My roots were negative 2 and positive 1 and 3. My end behavior was up on this extreme and down on this extreme. That needs to line up, but my board's off a hair. You understand that? So that's what we know. At the root negative 3, does it cross or bounce? Yeah, at the root negative 2, does it cross or bounce? It bounces. Now, notice it's coming from down below, right? It's coming from here, and then it's got to get down to here. So it's going to have to bounce like this if it's going to do that, right? And we may want to go ahead and connect that so we know we got that going on. What does it do at the root 1? It crosses. Now, it's coming up from here, so it's going to have to do like that, right? That's ugly. What's it doing at the root 3? It's bouncing, and it's bouncing, it's coming up at this point, and it's up at this point, and it's bouncing there, so it would have to bounce like that. You see how we got that? Okay. So we're graphing by looking at the x-intercepts, which are also called the roots, and determining whether they bounce or cross, and then looking at the y-intercept and also looking at end behavior. Any questions so far? Okay. All right, so we've dealt with an x squared, x cubed, x to the fourth, x to the fifth, and we're going to go back and end with an x squared. We want the end behavior. The exponent is even. That means they're both up or both down, the form of a parabola. The a is positive, which says they're both up. They're the same and up. They say we determine the end behavior. To find the roots, I'm going to set my equation equal to 0 because the roots are the values of x that would make y 0. I have a polynomial of the second degree, therefore I'm going to have two roots. I'm going to factor using the AC method. It factors, doesn't it? I didn't want to use up a lot of time if I'm going to factor. All right. So the AC method of factoring, the first thing you do is multiply your A, which is 2, times your C, which is negative 3. 2 times negative 3. Understand that? So my A is 2, my B is negative 5, my C is negative 3. I'm going to take my A of 2 times my C of negative 3, and I'm going to get a negative 6. Now, when I teach this, I try to make sure we are focusing on sign rules so we don't make any mistakes. The next step says, find all the factors of the AC answer. We want the factors of negative 6. So we would think 1 times 6 and 2 times 3. But I need to know that that needs to be a negative answer, right? And when you multiply with blank signs, the answer is negative. Same or different? Different signs. So since my 6 is negative, I need those factors to be different signs. Okay? So right now I'm thinking I want to find the factors of the AC answer negative 6, the factors of negative 6. Well, can I multiply to get negative 6? 1, 6, 2, and 3, but they need to be different signs to get a negative 6. The next step says, I'm quoting steps from my algebra book, page 213. It's in chapter 7 of my algebra book. The next step says, pick the pair that add to give you the B value using sign rules. So we're going to pick the pair that add to give us B using sign rules. Pick the pair that add to give you B using sign rules. Okay? So, we want to say our sign rules. When you add or subtract with, what about the signs? Different signs, I gave you a sheet yesterday, right? Subtract and take the larger sign. We have to know our sign rules right here. We're done. When you add or subtract with different signs, you subtract and take the larger sign. And I'm going to highlight that as I go. When you add or subtract with different signs, you add and take the larger sign, which needs to be negative. They need to be different signs and negative. Different signs with the larger negative. Different signs with the larger negative. So the 6 and the 3 need to be negative. Right? Different signs, larger negative. Which of those pairs gives you a negative 5? The 1 and negative 6. So we pick the pair that add to give us the B value of negative 5 using sign rules. 1 plus negative 6, the signs are different. You subtract and take the larger sign, negative 5. Pick the pair that add to give you B using sign rules. Okay? And then we're going to split the middle term into those two pieces. So we're going to change the negative 5x into x minus 6x. From that. X minus 6x. 1x minus 6x. So we have 2x squared plus x minus 6x minus 3 equals 0. All we did was change the 5x into x minus 6x. We still have the rest of that original equation. So let's review what we did. And this is on page 213. we multiply the a times the c, and we got a negative 6. And then we're going to find the factors of AC, which were 1, 6, 2, and 3. We think about our sign rules. When you multiply with different signs, the answer is negative. And then we said we're going to pick the pair that add to give us the B value using sign rules. When you add or subtract with different signs, you subtract and take the larger sign, which needs to be negative. And so we made our larger ones negative, the 6 and the 3, okay? And the pair that added to give us the negative 5 was the 1 and negative 6. The next thing we did was we split the middle term, negative 5x, into those two pieces, x minus 6x. And that's where we're at. Split the middle term into those two pieces. The next step says to factor the left pair and factor the right pair, and we will be looking for a common binomial that pops out. Out of the left pair, we can factor out what? An x. So we think x times y to give me 2x squared. 2x. And then x times y to give me an x. 1. So I factor out an x, and I have a 2x plus 1. What can I factor out of the right pair? Negative 3. Negative 3 times what is negative 6x? 2x. Negative 3 times what's negative 3? Positive 1. And we were hoping for a common binomial, which we got. If we didn't, it would not factor, and we would have to go to the quadratic formula, assuming their square root are imaginary answers. Okay? So now we're going to write it as the product of two binomials. The first binomial is that common binomial of 2x plus 1. And the second binomial is the pieces x minus 3. So it's factored, but we still don't know the roots. We know the factors. If the product of those is 0, then we could say that either the first one, 2x plus 1, is equal to 0, or the second factor of x minus 3 equals 0, and we would solve for x to actually find the root. Here we would subtract 1, divide by 2, and we're going to have x equal negative 1/2. On the other one, we're going to add 3 and get x equal 3. So my roots are negative 1/2 and positive 3. Everybody see how we found the roots of the quadratic? We use the AC method of factoring a quadratic. We need to remember that. We need to remember how to factor by grouping on cubics. We need to remember the difference between two squares. And we need to remember how to use the quadratic formula. Now, each of those appears once only. That's an odd number apiece. When a root appears an odd number apiece, they cross. Okay? The y-intercept is the value of y when x is 0. So if we put a 0 for these x's, they're going to cancel, and we would have a y-intercept of negative 3. Understand how we got the y-intercept? If we put the y-intercept is y when x is 0, so if we put a 0 in for those x's, it wipes all that out, and you're left with a negative 3. Okay. So we have a root at negative 1/2, 0. If if I can hit it. Somewhere about there. I have a root at 3, 0. I have a y-intercept at -3. That's big. Still big. It's okay. Yeah. My end behavior is up, up. And so I can see it crosses at each of those roots. And so I can see that it's going to do something like that. That's a little extreme on the vertex maybe, but I'm fighting board coordination. Any questions on number 5? All right. Good stuff. Appreciate your attention.